Hey everyone! So in today's video we're going to be solving an actual past paper question and we'll see how the concepts in the experimental chemistry that we have studied so far can be applied to the actual past paper question. See? So the question we are doing is from an exam of 2020. It is from summer and it's obviously a paper 4, so it's an ATP question. It says iron tablets are used to treat iron deficiency in the body. Iron tablets contain iron 2 ions which are Fe2+. A student does an experiment of titrations with aqueous potassium manganate to determine the percentage of iron in some iron tablets. Diagram of some of the apparatus the student uses are shown. So we have A, B and C. Name the three pieces of apparatus. So we know that A is a burette. Why is it a burette? Because it has this, it has this tap over here. B is definitely a measuring cylinder because it has graduation on it. And C has this bulb over here. So obviously it's a volumetric pipette. So we know that A is going to be a burette. B is going to be a measuring cylinder. And C is going to be a volumetric pipette. So a volumetric pipette. Now let's see. The student records the total mass of the 5 iron tablets, crushes the tablets, dissolves them in distilled water, and makes the solution up to 250 centimeter cube. So this is the final solution. Uses apparatus C. Apparatus C was the pipette to transfer 25.0 centimeter cube of the solution of iron 2 ions into a conical flask. Uses apparatus B, which is a measuring cylinder, to add 10.0 centimeter cube of dilute sulfuric acid to the conical flask. Fills apparatus A with 0.00500 mole per decimeter cube KMnO4. Titrates the solution of iron 2 ions with the KMnO4 until the first permanent pink color is seen in the conical flask. Repeats the titration. So one thing is clear for us. If we look at the overall picture that the student is doing, in the conical flask, there is a burette over here, and then at the same time, it is talking about complete a 250 centimeter cube solution. So we have a total of 250 centimeter cube solution, which was made by the 5 iron tablets, 5 Fe tablets. From the 250 centimeter cube, we only get 25.0 centimeter cube of the solution. So it's 25.0 centimeter cube of the iron solution. It has 10.0 centimeter cube of sulfuric acid, but we are not concerned with that because it is not going to participate in the redox reaction. And then from here, we are transferring potassium manganate solution. Now let's see what the question says further. The equation for the reaction is shown. Suggest why dilute sulfuric acid is added to the conical flask. So if you look at the question, you can see iron and manganate, which are both reactants, and acidic environment is needed. So to provide an acidic environment for the reaction, because the reaction apparently happens in an acidic environment where H+ ions are needed, and H+ ions can be provided by the sulfuric acid. Give the formula of the ion responsible for the pink color at the end point. So if you have watched the videos of redox, you would remember that potassium manganate is a solution which is purple in color, but obviously since it's diluted, it is going to help in determining the end point, because when the reaction completes, potassium manganate remains in the solution, the excess, and it gives us a pink color. So it is the manganate ions. It is called the manganate 7 ions. Manganate 7 ions. The diagram shows parts of the apparatus A with the liquid levels at the beginning and the end of the titration 3. So we can see the values over here. The initial value, if I am not wrong, for titration 3, let's feed it in. The initial value is between 0 and 1. So it is 0.5. If you measure this, it becomes 0.6, 0.7. So this becomes 0.7, the initial reading. And if you read the value of the final reading, it is just 1 unit after 17. So it becomes 17.1. The volume used can be found out by final volume minus initial volume. So 17.2 minus 0.0 would be 17.2. 16.9, I don't know the initial reading, but I know the difference is 16.7. So final volume minus initial volume is 16.7. The final volume they've already mentioned is 16.9. I don't know the initial volume, and 16.7. So it becomes 16.9 minus 16.7 is equals to the x, which is the initial volume. So initial volume becomes 0.2. What about the volume used in titration 3? It is obviously 17.1 minus 0.7. Now if we do that on a calculator, we're going to get 16.4. Now we want to take two best titration results which are very close to each other. So I'm pretty sure 16.4, 16.7 and 16.9 are apparently very close. But we can't use 3. So which two are more closer? 16.9 and 16.7, because they have a difference of only 0.2 units. Use the ticked value to calculate the average volume of 0.00500 mole per decimeter cube of potassium manganate. So average volume is 16.9 plus 16.7 divided by 2. So we're going to get 16.8 centimeter cube. A second student does another series of titration using the same method and the same 0.00500 mole per decimeter cube potassium manganate. The student obtains an average of 16.9 centimeter cube. The equation for the reaction is shown. Calculate the number of moles of manganate used by the second student. So calculate the moles of manganate. The formula for mole is CV divided by 1000. Now it's going to be, the concentration is 0.005. You might want to put the other zeros, but that is okay. And then times 16.9 divided by 1000. So what is the answer? The answer is going to be 8.45 exponent minus 5. So it becomes 8.45 exponent minus 5 moles of potassium manganate. Then it says, calculate the number of moles of iron 2 ions present in the 25.0 centimeter cube solution. We can't use that. We don't use this because this is just the volume. We don't have the concentration with us. So what do? We apply a ratio method over here, and the mole ratio that we can apply over here is between iron and manganate. We know that the mole ratio between them is 1:5. So manganate is 1, iron is 5. So if the moles of manganate was 8.45 exponent minus 5, we can find out iron by just multiplying it by 5. The answer is going to be 4.22 for me, 4. So this is the moles of iron ions for us. Calculate the total mass of iron in the 5 tablets. How do we do that? We know there's a formula for this. For this, we can do the moles times atomic mass is equals to mass. So mole was 4.222 times exponent 4 times atomic mass, which is 56 for iron, times is equals to the mass. So how do we get the mass? It's going to be 0.0237 grams for us. The total mass of 5 tablets is 1.83 grams. Calculate the percentage by mass of iron in the 5 tablets. You give your answers to 3 significant figures. So if you're going to be like, okay, the percentage is equals to the mass calculated divided by the total mass times 100. So the mass calculated by us was 0.0237, and the actual mass was 1.83 grams times 100. Now if I do that, my answer is going to be 1.83 times 100, 12.9%. So this is how we calculated the percentage of the iron in the iron tablets, and this is how we performed the whole titration question. So there's going to be an upcoming video, one more on the titration question, because here we even looked at the pieces of apparatus and some nearby like related questions. So we'll do more questions like that. Stay tuned, guys. So guys, we're continuing the same paper, and we are trying another question from the same paper to see whether we remember salt analysis, which was qualitative analysis, or not. So it is the same exam. It is you can see it is May-June 2020, and it's paper 4 variant 2. A solution contains one cation and two anions. A cation is a one with positive charge, anion has negative charge. The table shows the tests a student does on the solution. Complete the table. Name any gases that are formed. To a portion of a salt, to a portion of the solution in a boiling tube, add aqueous sodium hydroxide. The solution contains Fe2 plus ions. Now, if we remember, what would be the observation for Fe2 plus ions? It would be green precipitates. Those are insoluble in excess, right? So we can write over here green precipitates, which are insoluble in excess of obviously sodium hydroxide. To a portion of the solution in a test tube, add dilute nitric acid until no further change is seen. A gas is evolved that turns lime water milky. I know that a gas that turns lime water milky is carbon dioxide. So carbon dioxide is released. Why would a carbon dioxide gas sample would be released when nitric acid is added? So that is only for carbonate. So we have to mention that the conclusion is that carbonate present as CO2 gas is released. So the conclusion is that carbon dioxide gas is released, because they're saying at the beginning of the question that I have to mention the name of any gases formed, and then carbonate is present. If you remember, carbonate is, by the way, CO3 with a 2- charge. Coming back, keep the solution for test 3. Okay, add aqueous barium nitrate. If I remember, barium nitrate, BaNO3 twice, is a test reagent to confirm sulfate, and a white precipitate is formed definitely. So what is the scenario over here? It contains sulfate ions. So sulfate ion present. Sulfate is SO4 with a 2-, because when barium nitrate is added, barium sulfate white precipitates are formed. So this is how we completed a salt analysis small question. Let's look at another part B of the same question. It says calcium ammonium nitrate is a water soluble salt. Describe a series of tests and the observation to identify calcium ammonium and nitrate ions in a sample of calcium ammonium nitrate. Your description will need to explain how to prevent the ammonium ions interfering with the test of nitrate ions. Now, if you remember that each of these ions have a test that we have studied in previous video. So test for calcium should be something that we begin with. So let's talk about, in order to test calcium ions, what do we add? We add aqueous sodium hydroxide. So we add aqueous sodium hydroxide to the sample, and what happens? White precipitates are formed, which are insoluble in excess. So which are insoluble in excess aqueous sodium hydroxide. That confirms the presence of calcium ions. That confirms calcium ions. Now we can jump to ammonium ions. And when we talk about ammonium ions, we know the test for ammonium ions, we add aqueous sodium hydroxide and warm. So we can say we have already done the same thing. So we can say to another sample of the salt, we do the same thing. To another sample, add aqueous sodium hydroxide and warm. So when we warm it, a gas is released. Which is the gas? A gas released that turns damp red litmus to blue. Damp red litmus to blue. So ammonia gas was produced that confirms ammonium ions, because ammonia can be released by ammonium ions. That confirms ammonium ions in the sample. Now we have to talk about nitrate ions. So nitrate ion has its own test. We add aqueous sodium hydroxide with a piece of aluminium, and then we heat it and ammonia is released. But the problem is that they're saying this in the question as well. How do we make sure that the ammonium ions don't interfere with the test for nitrate ions? How do we confirm that? So what we can do is we can continue to heat and test it with litmus paper until no further change is seen. And once we can confirm that all the ammonia has been released, only then we add the aluminium. So currently we have sodium hydroxide and ammonia is being produced. So we can continue this test. We can continue heating. We can continue allow the release of ammonia gas. And then what do we do is, once the ammonia is released, then we go for it. So over here we can say continue heating the sample with aqueous sodium hydroxide. Let me write the A, yeah. Aqueous sodium hydroxide until all ammonia gas is released and litmus stops changing color. So no more color changes seen. Litmus stops changing color. So all the ammonium ions are used up, all the ammonia gas is released. So we can say until all the ammonia is released and until all the litmus paper stops changing color. Then add aluminium foil in the same sample. In the sample and warm. More ammonia gas would be released. Now, more ammonia gas would be released because this time this ammonia is coming from the nitrate, because previously all the ammonia gas was released from the ammonium ions and you had tested it, the litmus had stopped changing color, so all the ammonia was released. Now when you added a piece of aluminium foil and warmed it, suddenly new ammonia gas started coming out. So this more ammonia gas would be released, confirmed using new litmus paper, confirmed using new red litmus paper. So that indicates nitrate confirmed. That indicates nitrate ions, NO3 minus ions. So this is how we confirm a test for calcium, ammonium, and then nitrate in the same sample. I hope the two previous questions are clear for us, and the next video we'll meet with some new questions. Stay tuned, guys. Thanks again.